Hello. So for our spring 2020 senior project, we decided to build an interactive LED beer pong table. My name is Efren Yerena.
Hello, my name is Victor Ifegwu.
Hello, my name is Elias Sandoval.
And my name is Mwansa Sikanyika.
So our objective here is to build a project that students could relate to, and to make it a little bit more exciting, we decided to add a grid display and also an RGB pod sensor and a live scoreboard to keep track of the game. We split this, our approach was to split this procedure into three phases. The first phase was to do the PCB design, and then the second phase was to build the tables and the project assembly, which is putting the PCB and putting it onto the table. And the final phase, which is the software, is putting everything together, wiring, soldering, and also coding.
So for the table frame, this is basically the foundation of the project. To the right here, we have a 3x8 standard size beer pong table. The middle section is where the acrylic sheet would go, and it's about 1/8 in thickness. That's basically going to cover the sensors so that nothing spills over them and protects the lights as well. To each side of the table, we have a 1/2 foot rail, green rail. That's basically just for remove cups or bystanders. The main material that we used was plywood, and we added some pedestal legs on the bottom for support and easy setup. And the PCB hardware that we designed will also be attached on the bottom of the table. The master PCB. So this PCB is the brain of the entire project. We can start off by receiving 12 volts and 5 amps from our power supply into a 2.1 millimeter plug. As you can see on the picture here to the right, the master PCB will communicate with the pod controller number 1, pod controller number 2, and the LED grid controller. I'll go more into depth in the next slide regarding that. The grid controller runs at about 5 volts, and the microcontroller inside the master PCB runs at 3.3 volts. And to connect everything, we use the Cat5 cable in combination with RJ45 connectors. And one more thing would be the actual installation or programming of the microcontroller. We needed to use the software of MPLab combined with PicKit3 and a C30 compiler. There was many components on the master PCB, as it was the biggest PCB from all four, but I'm just gonna go over the key components here. So the first one is the PIC24HJ128506A, and it's a TQFP 10x10 millimeter 16-bit microcontroller. It has 18 analog inputs in this 64 pin here to the right, but we only use 2 inputs because one comes from pod controller number 1 and the second comes from pod controller number 2. It's important to note that timer 3 on the microcontroller served its purpose in the operation of the RGB pods and also the timing of our PWM drivers, which is about 60 hertz. TLC 5940, these are just PWM drivers, but I'll let one of my colleagues go more into depth in terms of their function because they're very similar. 74HC540, this is a 8-bit inverting or line driver, and we use this because it enables us to use current limiting resistors so that we can keep all of the circuitry safe for all of the different parts and components of the project, since we have varying voltages. So as you can see on the right-hand side right here at the bottom, I took a screenshot of the schematic for our switching regulator. You can see that we have 12 volts coming in, going through a switch. We added some capacitors, and we basically end up getting 5 volts so that none of our parts get damaged. And of course, we use a lot of SMD resistors, capacitors, potentiometers, diodes, and connectors. This is just a quick overview of how the master PCB works and communicates with the entire system. On the left-hand side, we have an individual pod sensor that's coming from either the master or the secondary side of the table. That's going to send a signal to either pod controller 1 or 2, depending on what side it is or what pod number it is, 1 through 20. It's gonna get into the master PCB as an analog signal, and then that signal is gonna be converted into data that's gonna communicate with the LED grid controller to ultimately display a number of the live score.
All right, for the design of the 32 by 12 LED display, it is made up a total of 384 LEDs. There are 12 LEDs in one row and 32 columns. And the way they're connected is that the anodes are connected to each LED in the row, and the cathodes are connected to each LED in the column. And then the way we go about controlling those is using a multiplexing and shifting technique. So the 32 columns are connected to 4 8-bit shift registers. The 12 rows are connected to 2 CMOS decade counters. And there's also transistors and resistors they were used to control the circuitry. And this is very practical because it condenses the wiring and can be controlled easier with an Arduino Uno. So here's a picture of the Arduino Uno that we're using for this project. Using the Arduino Uno, we're able to code display scrolling numbers, the score of the game, and cool animations. Only a total of 5 digital input-output pins were used, and power and ground are provided by the master PCB. Here are the schematics for the way the columns and rows are controlled. So on the left side, we have the 4 8-bit shift registers, the 74H595Ns. They're all connected in a cascaded form. And on the outputs of the chips, there's resistors corresponding to each column, which is just controlling the current. Then on the right side, we have the 2 CMOS decade counters that are controlling the rows. And again, they're cascaded. 2 chips are cascaded together, and then the transistors serve as a purpose for switching. So depending on what rows need to be activated. And then tying it all together with the master PCB, the way the Arduino is configured to communicate with the master is by a serial peripheral interface. That way we can set up the PIC and the Arduino in a master-slave configuration where data can be sent and received simultaneously. And the reason we want to do that is so we can update the score from the pods to the pod controllers in real time, so we could display it on the screen. And in order to do this, only 4 connections were needed, and some code for the master and the slave is needed as well.
So this is one of the basic but also important component of our design. These boards, we want to be able to detect what's on the table and also add some visual effects when cups are detected on the table or otherwise. So to be able to do this, we design each pod consisting of 4 LEDs and an infrared sensor. And to control these functions, we're going to be connecting these pods to a controller. We're going to have 2 of them for 10 of each pod separately on the right side of the table and on the left side of the table. So the design of our pods was based off the size of the cup. So we extended the width based to the 57 millimeters width of the bottom of the party cups usually used to play these games. So we extended it to 60 millimeters to comfortably sit the cups. The next slide here is the pod builds. So as you see on the screen, this is my schematic. The first component of my build was the 8-pin head. This is where we're gonna be giving the signals, and also receiving output signals from our sensors and also to our transistors as well, and also power. So the first pin, we have a female. We have also the transistor. The transistor is what's gonna detect what's on the table and then also send a signal out to the controller to let it know there's something on the table, and then either to turn it on and then get a return to the transistor to turn on the LEDs or turn it off. The transistors here just acting as a switch. So we have our LED, we have RGB LED. So we have each transistor for each colors, red, green, or blue. And then the final components are the resistors. We have a 150 ohm and we have a 270 ohms. This small resistance are used as current limiters. And then the 39 kilo ohm is just a voltage divider to be able to read the output voltage from the sensor. And the final part here, as you noticed on the previous slide, I designed the PCB through Eagle, and these components are based off what was available on the software. So these components here, I would pick to make our design look more elegant when we put them on over the glass, on top of below the glass, to look more presentable and nicer. So we used a software mount for most of them. We didn't want to use a regular resistor acrylic ceramic one. And also, so this is just the amount of this components that we need to be solid onto the PCB.
Okay, this is my part. My name is Mwansa Sikanyika, and I'll be talking about the RGB pod controllers. So pretty much there are two RGB controllers, one being the master RGB pod, and the second being the secondary RGB pod controller. So pretty much how that works is one is controlling 10 pods on the left side, which are the RGB pods, and another is controlling the other 10. And with that, we have IR sensors on each RGB pod. So when a cup is detected, this RGB pod is going to have sensors that detect the signal, sending it in as a digital signal. And this signal is then sent to a multiplexer. A multiplexer pretty much has enough pins to withstand the incoming signals from each IR sensor. So when it detects that, it'll activate one pin, and that pin sends that signal as an output, and then it goes into our PWM driver, and this pretty much gets this digital signal, passes it through a low-pass active filter, which will actually help turn the signal into an analog signal. And then with that, we're able to work with the duty cycle, which will be between 100% to 0%, meaning we want it on or off for the LEDs. And then for the parts we actually used is I used 5 parts to actually build this. So the first being the multiplexer. The multiplexer we were using was a 7-Force HC4051. This pretty much is attached to 10 IR sensors coming in as signals, and it sends this information from each pin, depending on which one is active, and sends it out as an output. And then it sends this to the PWM driver, which is the one you see at the bottom left, which is the TCL5940. And this pretty much receives the signal as a digital input from the multiplexer, passes it through a filter, and gives it out as an analog signal, which is how we work with the duty cycle. And then we have the pin headers, which my colleague Victor earlier talked about, and he went more in depth with it. It's pretty much just an electrical connector. And then we have resistors in this circuit because we need to limit the current that's going through the circuit. And then we have capacitors that pretty much hold and store energy for the whole project. And then lastly is how I explain how RGB pod controllers are pretty much middlemen to the project. So they work with 2 parts, the RGB pod and the master. So they're pretty much passing data from the RGB pods and sending it over to the master. The master is pretty much a part of the project that's like the most logical. It makes most of the logical decisions of the project. So first we get this detection from the cups. It's sent in through the same whole process I just talked about, where it sends it through the multiplexer. Multiplexer multiplexes this signal, sends it out as one signal, sends it into the PWM driver, and then this driver now finally sends it out to the actual master pod controller. And then from there, this actually decides which type of lights are gonna go on based on the score of the game. Here are a few parts I actually implemented into this pod. So we have a driver, we have a multiplexer, we had some jacks, a quad, single, and a dual. We had 2 headers, a 9 and a 2 pin. We had some resistors, we had capacitors, and yeah.
So for the software, we coded everything in C just to keep things simple. In this slide, I'm going to go over some of the functions that were very critical and important for the code to help the project come to life. The first one would be the sensor calibration function. So this function, what it's doing, it compares a preset calibrated value for each IR sensor, and it compares it to a real-time ADC value. Now, if there's a drastic difference or a drastic change, then that means that there's a cup over the sensor, hence we have a detection. A detection can be thought of as a 1 or a high for the code, and no detection can be a 0. The goal of the software, again, is just to tally the amount of cups on each side and display the correct number. So to do this, we need to update the IR sensor values inside our main loop. We do this through storing our values in the 16-bit unsigned integer called byte, which I will discuss more in the next slide. And we also created an array of 12 hex numbers, which basically represent rows 0 through 11. And here are some of the functions. Update sensors, I mentioned, will be in our main loop to refresh every second so that we can update the live score. We set the byte equal to pack sensor data. That's kind of what allows us to figure out exactly what would be the matching number. And then the ID scoreboard function is the overall software for displaying the numbers. So as you can see here to the left, I drew out a schematic of our 12 by 32 grid. The way this works is, for example, let's say we're going to display the number 10. As you can see in the array, the first and the last element consists of 4 Fs, meaning that they're all ones. This is due mainly to create the frame that encaptures the number in the center. And then all of the other bits or grids would be either 1 or 0s based on whether the LED should be on or off. So this way we can display numbers 10 through 0.
All right, and here is a table of our projected schedule, and to kind of follows along with the phases. So like the first phase, the first couple dates were involved with the PCB design and ordering components. And then after that was a table creation, so building a frame. And then once we built that frame, we could create the LED display. And that's already towards like February, the end of February right there. And then unfortunately, due to the COVID-19, we've had changes in our design, slight changes that involved us ordering different parts or more parts, and shipping kind of drastically changed. So that kind of affected our schedule, but we still worked on the software, although it's hard to test something when you don't have it made. And unfortunately, we've just been working individually ever since then and just doing everything we can.
Costs. So the cost is pretty much a main part of the project because you need to invest in yourself for you to actually do the project. So here we have exactly how much you spent, not exactly, pretty much an estimate of how much we spent on each part of the project. We have components, LEDs, and PCB manufacturing. That totaled out to $300 for $100 each. We have the Cat 5 cable, which is $50. We have the ping pong balls, which are $10. We have the plywood and the acrylic sheets for $120 each. And then we have the prosthetic legs for $30. And it came to a grand total of $630. Thank you so much, and I hope you enjoyed the presentation.
Bye-bye.